And for those who raised their hands yesterday, this will be a brief overview. We do have a poster up in the cafeteria room where you can get more details about the algorithm itself and the initial results that were presented last year. So CAL means context-aware learning, and that will be a theme that keeps recurring as I go on. So I'm going to just touch on a few of the points that we have worked on in the last year. One is to look at how this plastic synapse population evolves, namely the number of synapses, the number of connections that are being made as it learns. I'll illustrate how well it learns from just a few examples. And then I'll touch on the absence or the minimization of forgetting, which is one of the main goals that we have. So this is the sort of big picture view of how CAL is put together. We think of it on 4 length scales. One is the neuron itself, which has a body and multiple dendrites in blue. I've drawn them in a geometric way because there's axons coming in, and that's the red axons coming in from below, from lower down in the network with feed-forward input. There are lateral connections and there are apical connections coming from regions above. So this, the main distinction among these dendrites is, first of all, they're doing the integration. The computation, if you like, is on the dendrites. And they're in 2 kinds. The basal ones, the ones coming from below, are directly driving, provided that the modulation provided by the lateral and apical dendrites are going to allow that neuron to fire. And then the data out of that, the firing, is propagated through axons that can go either up laterally or down. The next scale is the microcolumn, mini-column, which is probably familiar to most of you. That has one sort of master neuron at the bottom that we attribute to the L4 layer of the cortex. So this connects then to an array of neurons going up the column. And the definition of a column in this picture is that it is all the neurons that connect to this driver down here. So it's, everybody draws it as a vertical column, but if you look at the micrographs of a real brain, they're sort of scattered around a bit. So the definition is really just the connectivity. And these are interconnected laterally, and as you will see, that allows us to build a kind of recurrent neural network, what we call sequence memory, that learn sequences. And these columns are arranged in sheets, little pieces of the cortical sheet with multiple columns. And we're really focusing on this L4 neuron that forms then a 2-dimensional plane of neurons, and all the columns that go above them. And then, in addition, there's an array of apical synapses that we attribute to the L1 layer of the cortical sheet. And then on the largest scale, these regions, these rectangles in this diagram, are arranged in levels of a hierarchy. So the lowest level gets input from the senses. So this would be the sensory part of the cortex. They feed forward to the next layer and so on up the hierarchy. Each level feeds forward to the level above, but the higher levels can feed back to any level below. So that in an overview of the architecture. And I want to highlight how this differs and why it differs from deep neural networks and all the variants of that. So first of all, oops. this is going forward instead of backward. There we go. First of all, in deep neural networks, the neurons have to be essentially analog. I mean, they have a sharp threshold, but it has to be differentiable. And so the data representation is in the form of compact real vectors. Cal uses binary neurons. They either fire or they don't fire. So zeros and ones. And they are sparse. That is, out of any given set of neurons, a relatively small number fires at any given time. Deep neural networks do backpropagation of errors in order to minimize a global cost function by some kind of gradient descent. In Cal, the learning is strictly local. It's a Hebbian learning rule modified in ways that I'll describe. But basically, neurons that fire together wire together. So it involves two neurons, one synapse to implement the learning. In DNNs and related networks, the connections are defined initially to a very large extent. There are exceptions, of course, but the network design says which connections are made. In Cal, very importantly, the topology is plastic. Synapses are generated, that is, a connection, maybe a weak connection, but a connection is made, and then it is updated and perhaps removed in response to the data flowing through that pair of neurons. So the consequences of that are slow learning, large data sets, and sometimes catastrophic forgetting. So this is really the goal. We want to overcome these shortcomings of conventional machine learning. On the other hand, Cal learns rapidly in real times with relatively few examples, and I'll show you how we can retain the memories without much forgetting. So previously, we demonstrated correlation. And that's a very simple consequence of the Hebbian rules. First of all, if neuron A fires and then B fires, so there's the input axon and B on the dendrite, then this is strengthened. But if A and A prime fire at the same time and B fires, then they both get connected. Therefore, the mutual connection of A and A prime is reflected in the output B. So this is a sort of coincidence detector, a phrase been used before. And then the inference that that correlation exists is in the firing of B eventually. I mentioned sequence learning. That proceeds in a very straightforward way. So if neuron A fires, and it contributes then to the prediction of B. Maybe there's a lot of A's, but I'm trying to simplify it here. So B is now predicted. That's a modulation, but it does not fire. It's lowering of the threshold potential, depolarization, however you want to phrase it. If then X at the bottom of the mini column fires, then B fires preferentially. The other neurons in the mini column are effectively inhibited by the firing of B. So that verification then is fed forward. Doesn't say it here. So the verified signal from B is fed forward, and the synapse between A and B is strengthened. So now we've memorized the subsequence, the part of the sequence that is A and B, and then in turn, B's activation may contribute to the prediction of some C further on in time. So in that way, sequences get learned. So I ran out of time last year to tell you this, but this is a very important aspect. So out of that algorithm, stable representations are spontaneously generated. So it's an emergent property of the network. And this also is an illustration of scaling. So to a small hierarchy with 15 regions on 9 on the lowest level and fewer as we go up. And this network was fed a number of shapes, binary images, or one frame of a movie clip is a binary image. So this is a sequence of binary images in a video clip. The verified predictions are fed forward up the hierarchy where they're temporally pooled. And for us, temporal pooling means that there's a union of a successive sequence of feed forward. So successive verifications, and 2 or 3 are enough to generate this stable output. So by the time you get to the 4th level, so what I'm showing you here is a subset of the column indices. So this is showing the active columns as a function of time, if you like, or iteration. So each one of these shapes, there's 36 iterations, and you can see while the shape is being shown to the very lowest level, the 4th level has a stable output. So that is a representation. Basically, these bits that are on in this vector are representing a rotating square or a rotating triangle. That's a semantic meaning of that representation. And then you can compare the activity during the input of a square with the other iterations during that square, and so that shows it's stable. And the brightness down here shows the stability. Pentagon is not quite stable. In fact, that's oscillating between hexagon and a hexagon and a square. So it's somewhere in between. And if you look at this, this is not a confusion diagram. It's not trying to classify, but it is showing the similarity and the orthogonality between the shapes. So the last thing, the talk last year, was to propose a method to avoid forgetting. And that was to use in the decrement or the anti-Hebb updates of synapses, a nonlinear magnitude in the decrement. So this is a relative decrement, such that by the time you get to maximum weight or maximum permanence, and I'm going to use them interchangeably for the time being. By the time you get to maximum permanence, there are no decrements anymore. Therefore, at permanence 1, you start to establish a population of tenured synapses. They're in their place forever. So I'll come back to this. So what have we done new with Cal in the last year? First of all, we've got away from binary synapses. Neurons are still binary. The synapses now have some adjustable weight. And we looked at several different number of bits to represent the weight of the synapse. Sort of saturates, as you see, at about 4, and that's not very different from full double precision floating point, of which 48 bits are being devoted to the magnitude, mantissa. So 4 bits may be a kind of a sweet spot. I mean, it doesn't mean it's there forever, but everything I'm going to show today is based on 4 bits. And that's kind of intriguing. If you think about the geometry of a synapse and how many ion channels there are, typically there's a few dozen ion channels. That's what there's room for in the in the bouton of the axon that comes in. So it's not a bad number, and it sort of corresponds to nature. And that may also then, if we really make a hardware implementation of it, allow some sort of hardware acceleration. The second change is we now initialize with no synapses connected whatsoever. So this is not a baby that's born with too many synapses. This is a fetus in the womb that is developing from having no synapses at all and already starting to make them in response to whatever stimulation it gets. So this is actually not driven so much by neurology, but driven by computational efficiency. We don't waste time removing synapses that are not relevant. All the synapses that are generated then have some degree of relevance, and then will either get reinforced or not. And then, since there are no synapses on the axons, we have to decide how to connect them. And the part of the algorithm that covers this is to connect to the dendrites that are the most ready to make new synapses. That's the dendrites that have already the fewest synapses. And this combination leads to faster and more accurate learning, and I'll quantify in a few slides. So let's think about this plasticity. There are three phases that we can identify in the making and strengthening and then pruning of these connections. So this diagram illustrates the number of synapses in blue starting from 0 at iteration number 1. And it initially starts growing and then accelerates, so there's some upward curvature. So during this phase, it's essentially making new synapses all the time. Anytime it needs another synapse, there's plenty of places to put it. So this is predicting a sequence. It doesn't matter really what the sequence is. But the first correct prediction of the sequence is made at iteration 30. And by iteration 300, it's reached 95%. So that's what I mean by rapid. There's relatively few observations of the input data. Phase 2, the rise sort of slows down a little bit, and there's an inflection point in there. And we can identify, it's still making new ones, it's still rising, but it's starting to remove irrelevant ones. There's some competition for places on the dendrite to put new synapses. So some of them are getting removed. And while that's going on, interestingly, there's a little bit of loss of accuracy. It's sort of rearranging the relevant synapses to make best predictions of the incoming data. And then phase 3, you start to see pruning of the synapses, removal of the weakest ones, the ones that are becoming less and less relevant. So after the 10,000 iterations of this particular run, we see a distribution that looks like this. So this is the 4-bit distribution, so there are 15 levels here. There are quite a lot that are permanent, so they're going to remember that sequence now forever. And the rest of the population is sort of tending towards 0 and eventual removal. So I want to make a comparison with a conventional recurrent neural network, an Elman neural network. So the task here is chapter 1 of Alice in Wonderland. I should say characters for us are a convenient abstraction of an event. So we encode a character into an integer, binary, sparsify that representation, and then we can read it. It's a sort of convenience for us humans who don't read binary. So this is hard because it includes spaces, all the punctuation marks, all other white space characters. It's in the phrase that was used by the Intel people, it is batch size 1. One input per character, and we predict the next one. And the metric is the percentage correct. No negative log likelihoods or bits per character or any of that. How often do you get it right? And this is done in one single region of Cal. So we have a sequence memory, but no hierarchy, no feedback. So here are the results for the first chapter, 11,000 characters. Cal starts to make correct predictions very quickly, gets to about 20% relatively soon. That's the next click. And gets even higher, 40%, and sometimes peaking more. And this is averaged over 100 iterations per point, or moving average, to show you that this is really driven by the input data. And take my word for it, if you look closer, this is rising where it's more or less narrative, straight text. And these drops come when there are conversation punctuation marks and stream of consciousness with dashes and all sorts of other punctuation. So this accuracy of averaging around 40% is 2.5 times more than we had a year ago. So that's the big advantage of the algorithm changes that I described. If we compare that with the recurrent neural network that is not operating the best way for a recurrent neural network, it's also batch size 1. It's minimizing cross-entropy loss function. And it very quickly gets to 20% as well, but then never gets any better. And part of the reason for this is about what is really being learned. And it illustrates this aspect of, I've got 2 minutes, well. So Cal predictions are clearly based on context. That is, it's starting to learn short words and ing, the sort of ending of the common words. Whereas the recurrent neural network sees mostly spaces. There's 18% spaces, so it gets to 18 or slightly more by predicting nothing but spaces. And then the next most common character is a T. So this is the statistical nature of learning in the recurrent neural network. Whereas Cal is learning in context. Space comes at the end of a word. ing, space, and space, of space, even after 50 iterations. So I'll speed up a little bit. I've said that RNN is based more on frequency than context. And learning fast is important. If you remember, 2 years ago, early version of this code taught Kate, this robot, how to walk. If Kate didn't learn how to stay upright in 20 steps, it was going to fall down, and well, that's the or else. So I'm now going to talk about retention of memories using this algorithmic trick of reducing the decrements in anti-Heb. So I'm going to make 3 networks. Each of them is going to start with a different task. So these networks are distinguished by what they learn first. One network has an easy task, a random sequence of length 100, and it gets 100% accuracy after 10 epochs. It says my time is up, but I'm going to use a few more minutes to go through this. The second network, network B, gets a moderately difficult task. It's sentences, just three examples of a short sentence, but they're given in random order. So that leads to 87% accuracy after just one pass through these sentences 34 times. And the hard one is Alice in Wonderland again. So then each network is asked to do the other tasks in sequence. And here are the results. So that's the layout of the tasks again. Network A learns the easy task first, gets 100%. Then it is asked to do tasks 2 and 3. It doesn't do so well as the 87% and the 40% initially, but it does not too badly. And then it does task 1 again, it gets 100% again. Then task 2 or 3, and now it's learned them. It doesn't get much decrement between the first time it did task 2 and the second time, and still task 1 is 100%. Network B learns the first task, gets 87%, and then when it comes back to that again after doing 3 and 1, it's still in the 80s. A little bit of a decrease, and then a little bit more when it comes back to it a third time. C, same sort of story. It gets this 40% immediately, a little bit of loss after doing task 1 and 2, but when it comes back to 3, it's comparable to the first time it did it, and the third time through, comparable again. So there's little or no drop when the network, the appropriate A, B, or C network, returns to the first task that it learned. They're small change. It can even be positive, like here, where it gets better the second time through. So returning to the other tasks. So Cal is certainly not forgetting catastrophically, in this example anyway. It is what I would call a graceful forgetting, sort of gentle aging. There is, however, a loss of capacity, and what we have to study is just how many tasks can be learned. This was based on our experience of learning one task, what size network is needed for a single task. So we clearly need to increase the size of the network. So capacity is an issue. So my conclusions. Memories are clearly retained in the synapses. That's the a common conclusion in neurology these days. The memories are generated by neural activity and then retrieved by neural activity, passing data forward through the connected synapses. Synapse plasticity is illustrated structurally. That is, the topology of the network changes as new connections are made and perhaps irrelevant ones are removed. There's weight plasticity, where the weight is adjusted, again, based on local neural activity. So that is the correction mechanism, if you like, the error correction mechanism in a Hebbian network. And then you can remove plasticity altogether, right? When it reaches full permanence, stop adjusting the weight. That leads to faster learning, and clearly in context, and that context, as I said at the beginning of the talk, is given by the modulation of the dendrites, the fact that some dendrites are modulating as opposed to driving, that separation. So I'll end with a quote that I heard just this past weekend. I went to a play that was about the life of Turing. Not the movie, and not even the script, anything like the movie. But I think the same name, Breaking the Code. And this was a line not uttered by Turing himself, but by his bureaucrat administrator at Bletchley, where the Enigma team was working. So it's important to make the right connection. So I acknowledge various collaborations that we've had, and thank you for your attention.
Thank you, Campbell. We have time for one question.
Yeah, thank you for the talk. Enjoyed it. I have two quick questions, actually. The first relates to the architecture slide that you had. Yep. You basically talked about layer 4 and 1. Sort of what exactly are you modeling within those layers?
So these are layers that neurologists identify in the cortex. And so for us, layer 4, where the input goes, is a single layer of neurons, each with a basal dendrite. And that dendrite axon intersection, the matrix of these synapses, is our binary correlator.
Okay.
And the layer above is sequence memory, where the lateral connections lead to a recurrent network.
Okay. And the second question has to do with why did you decide to sort of move from synapses that are binary to not binary? What's the rationale for that?
Mostly because we were asking ourselves, are we limiting our accuracy of prediction? Is binary too coarse-grained? What if we have more bits? Do we get better predictions? And the answer is yes.
Thank you, Campbell.